Hello, today we're going to be talking about the Laplace transform. And this is an introduction video for the Laplace transform, so I'm really not going to talk a lot about the details of the Laplace transforms, but rather the why of the Laplace transform. So the idea of a transform is a trick in math. The trick in math that we always use is transformation. And the idea here is that, if a current problem is in a form that's complicated or just not doable and not easy to solve, the idea is rather than go do the hard way, find a way to transform to a new format. And these, again, are just general ideas. There's nothing mathematically concrete here. But that's the notion of Laplace transform. One example of such a transform would be like a U substitution. And U substitutions, again, you take a hard integral and U sub. And once you do the U sub, it becomes easy. And that's a good example of something you may be familiar with, where a transformation can really dramatically make a problem a lot simpler. All you have to do, all you have to do is find that way. So a Laplace transform is a similar idea. Okay, so the idea here is U substitution is where you're doing a change of variables. Okay, so change of variables, and that's the idea. You go from x, let's say, to some u of x, right? And by doing that change of variables, you're able to make a hard problem a lot simpler. With Laplace, the idea here is you might have a function f of t, let's say, and what you're going to do is transform to some other function, which I'm going to call f of s. And it has a new variable, and maybe this is the old variable. But the difference is we're not doing a simple change of variables. We're actually doing a change of functions. Okay, so the idea here is we're going to call the transform. We're going to give it a name, a symbol, and it's called, it'll be a script L, a cursive L, capital, of a function f of t. And that'll be the input. And the output is going to be capital F of s. All right, and so this has a very specific form, and I'll just write down what the actual computation is. It's going to be the integral from 0 to infinity of the input function, f of t, times e to the negative st dt. So it's an improper integral, okay? And s is that new variable. That'll be a new variable, right? And the idea here is that it's a parameter in the integral. Okay, so that the fact that it's a parameter in the integral means that there's actually there's many integrals. All with different s values. Okay, so for every single one of these integrals, if I change s, I change the integral that I'm computing. And so you actually have to worry about this new variable. You have to make sure that the integral actually exists. So let's just write it up here again. Change pages here. We're going to write down that Laplace transform again. And I can write it with of s, that's the new variable. That's going to be capital F of s. I'm going to write it down again, 0 to infinity, times f of t e to the negative st dt. All right, so again, this looks fairly exotic, but one thing we have to always ask ourselves is this is only valid it's only going to be valid for s values where the integral exists. If the integrand diverges to infinity and the integral diverges to infinity, then the function simply doesn't exist for that s value. So we'll look at some examples of this. So I'm going to actually just start with an example. We'll start with a function, a very simple function, just 1. Okay, we can do an integral of that one. 1 times e to the negative s t ds. Now recall that s is now a parameter in this integral. And what we're going to do is we're going to compute the antiderivative, which is going to be 1 over s times, it's a negative 1 over s, e to the negative st, and we're going to evaluate at 0 to 1, and that's going to be, 0 to infinity, my bad. And of course, here we have to write a little bit, we have to actually put a little asterisk here. Again, the idea that it only is valid for s values where the integral exists. If this integral exists, it means that this has to be not infinity. So we actually have to put a restriction on this. S has to be greater than 0. 1, because we have this division by 0 there, right? But also we want, I'm going to put it right there, we want e negative ts to decay to 0 as t goes to infinity. Okay, so that's really important that we make that proviso right there, that s has to be greater than 0. Okay, so if s were negative or 0, the function simply wouldn't exist. Okay, right, with that proviso then we can find out that it's going to be 0 minus a 1 over s, minus 1 over s e to the negative s times 0. We can, after doing all the math there, you find out it's just equal to 1 over s. Okay, cool. Now, let's try another one. Now let's try a function, Laplace transform of t. Think of 1 here as actually t to the 0 power, so we're really just doing t to the first power here. Now we can integrate this. All right. So this is going to be computed by integration by parts. So again, we're going to have a negative 1 over s times t e to the negative st. We're going to evaluate that at 0 to infinity. Now we're going to go plus 0 to infinity. I'll put a little boundary there to separate my work. 1 over s e to the negative st dt. So that's computing integration by parts. We can see this, if we do the similar limits of integration here, we actually get a 0 minus a 0. But we have to have that assumption then, the same assumption as before, that s is greater than 0. And that's very important that we state that. Right, finally, we're back to where we were before. We can take the antiderivative of this, and that's going to be 1 over s squared, right? Because again, s is a parameter in this, and so we're going to kick out two 1 over s's to make 1 over s squared, e to the negative st, and then we're going to evaluate it 0 to infinity. We're going to go plus there. And that's going to be we'll have to have a minus there to make the antiderivative work. And we see right there that that's going to be, once we take the limits of integration, that's going to be 1 over s squared. Okay, so I'm going to do one more here real quick. What about Laplace transform of t squared? Well, I won't do the full calculation, but I think we can see a pattern here. If Laplace transform of t to the first is 1 over s squared, and this is 1 over s, this is actually going to be something s to the third power. But it turns out we're going to get, if we do the integration by parts, you'll see that it'll be a 2 there. And now I'm going to go even more general here. If I take the Laplace transform of t to the n power, where that's any positive integer, we can find out, if you just do the calculation, it's going to be n factorial all over s to the n plus 1. As you see, in all of these examples, the power of s is just 1 more than the power of t. So all those are now understood Laplace transforms. Okay, so we've done a few basic calculations here now, but it still begs the question, who cares about Laplace transform of f equaling to f of s? What does it do for us? So the answer is that the Laplace transform is useful in the following ways. So I'm just going to write down a few of them. Solutions to linear DEs of the form Lx of t, okay, is equal to f of t, okay. 2, another way it's useful is in signal processing. So that's a science application in engineering. Application. Okay, and finally, Fourier analysis. So Fourier analysis is highly related. It's related to the Laplace transform in a very direct way. Okay, in fact, you can think of Fourier and Laplace are being 2 companion ideas that go together. They really are variants of the same idea. Okay, so what we're really going to focus on in this particular lecture video is this first one. This is a very direct application. So again, we could have a problem like a mass spring system where there's a mass, and then there's also a damper, and they're attached to some sort of anchor. We have a mass that's rolling on maybe some frictionless little wheels there, and we want to know x of t. We want to know the motion of that mass, and we might also be forcing it with some forcing function. So the example of this, the differential equation, the Lx of t, would be the mass times x double prime, so that's ma, mass times acceleration, plus c. So c in this particular case is that dash pot there, or that damper, times the velocity of the motion, and that's the force dependent on the velocity that's related to the damping and the damping coefficient. And then of course k, the spring constant, times the position of the mass with respect to where the spring's neutral position is. And of course all of that has to equal to the external forcing of the system. Okay, so most DE's students solve this with the method of undetermined coefficients. Okay, and I think some people just call that MUC, method of undetermined coefficients. Okay, and that works, or I should say MUC works for f of t that are of the following forms. One, they're polynomials. Two, exponentials. And three, trigonometric functions. So something like sine 3t, and exponentials could be something like e to the negative 2t, and polynomials, that could be something like t squared plus 1 minus t, for instance. Okay, that works well. But for a general f of t, we have to use Laplace transform. And in particular, functions that have jump discontinuities have nice solutions. And we can get those solutions very well. And so jump discontinuities are actually very important. In many real-world type instances, the type of forcing that's really important are things that have sudden shocks, sudden changes, like hitting the mass with a hammer really hard. That's a force that's very, very brief, but very, very, very intense. The other examples would be to instantly turn on a force and hold it on afterwards. So that would be another jump discontinuity type thing. Forcing that has that nature can be handled very easily with the Laplace transform. Okay, so in the final bit here, I'm going to talk a little bit. In the last little bit here, we want to know if I have f of t and I want to take the Laplace transform and it becomes this f of s, the question then is what is s? And specifically the units. Okay, and this leads us to the final concept I think you need to have in your head when you're dealing with this function, because a lot of people just don't get what f of s is. What is capital F of s saying? How does it relate to f, little f of t? And the answer is pretty straightforward. Recall that in transcendentals, they only really accept dimensionless units. Okay, so for instance, e to the RT, like that. So here's some examples. E to the RT or sine omega t. RT and omega t are dimensionless. And so if t is in units of time, that would then imply that r and omega have to have units of 1 over time. Okay? So units of 1 over time. So units of 1 over time, they're often called rates or frequency. All right, so if I look at this function then, if I look at the Laplace transform of f of t, again, I'll think of that as time. Okay, then the Laplace transform, capital F of s, which is equal to 0 to infinity of f of t. We're integrating over time. We're integrating over time. That would imply then that s is a 1 over time units. Okay, so oftentimes f of t to capital F of s is considered transforming to the frequency domain. So think of then as f of s, and it should also be noted then that basically there's a one-to-one correspondence. It's transforming to the frequency domain, and we can also go back. Okay, so if I have a function in the frequency domain, there exists a function in the time domain that it corresponds to. Okay, and so the last little bit is, okay, if we have a transform f of t equal to capital F of s, the question is there a inverse transform? And the answer is yes. It's not as easy to write down, but we can do it. We can actually then give it a name, Laplace Transform inverse of capital F s, and that gets us back to f of t. Okay, so this inverse transform that we know it exists, it actually can be written down. It's pretty complicated though. So I'll write it down for you, but just stress that if you're watching this video, you're probably not at the mathematical level. You don't have all the mathematical knowledge that you could actually find, that you can actually compute this thing. But I'll write down it for you. It's 1 over 2 pi I, the integral of c minus I infinity, c plus I infinity of f, back up, capital F of s, e to the s t ds. So this is what they call a Bromwich integral. And it's a line integral in the complex plane. Okay, so obviously this is something that if you're a differential equation student, or if you're a calculus student, you probably don't. This is probably well beyond you. This probably is a very unfamiliar concept, but the idea here is that you can actually compute these calculus objects, these integrals in the complex plane, and this is for some c value. And it goes beyond what we can talk about here, but there's your c value, and this is the real axis, and that's the imaginary axis. And you're taking an integral, a line integral, just the way you would take a line integral, say, in a third semester calculus course, and you're going up to I infinity there, positive I infinity here, and negative I infinity there. So you're integrating capital F within the complex plane. All right, so this is, of course, this is beyond most DE students' knowledge. But I'm planting the seed here that these things are pretty interesting, and they're very fun to do, and it's really fun knowledge to learn, but you don't have it quite yet. But we can compute L inverse is done by essentially just reversing known transforms. So, for instance, if I had a f of s is equal to, let's say, 6 over s to the fourth. All right, I'm going to see that n factorial equals 6 means that n is equal to what? 3 times 2. Oh, so it's equal to 3, sorry. All right, so clearly Laplace transform of t to the 3 power is equal to 6 over s to the fourth. Right, and that implies then the Laplace transform, the inverse Laplace transform of 6 over s to the fourth is simply t to the 3. Okay, so that's my my just big overview. We'll do a little bit more overview in the next video on why the Laplace transform.